Then we are doing a plant in Gujarat that is Eagle Fibers. Here we are doing power, cogeneration, and trigeneration. It's a complete heat utilization for the process itself. It's a synthetic fiber spinning plant, and here we require cooling as well as heating over here. And this is one of those examples where you have the maximum utilization of energy resources, and I think that is the way to go on the long run, because our resources are going to be scarce and we have to use them intelligently. Alliance Fiber is another plant. Here we are supplying 3 engines, one 12-cylinder engines. It's about 1 megawatt and 2 1.5 megawatt engines, also with a cogeneration and trigeneration concept over here. So as you can see, India, the energy utilization, and the customers also have become aware of that they have to use these resources intelligently, otherwise it will be not very economical for them. So these are some of the very good examples which we are doing here in India. This is the hospital once again on the gas side. Then here's a hospital in Germany, in Bayreuth, where we are also doing trigeneration plant over here. Then we have our own MTU plant in Friedrichshafen, where we are having 1.85 megawatts and thermal output 2 megawatts. So here we are using our own engines to produce power and energy for our own factory. This is another plant in Friedrichshafen. Friedrichshafen, there are about 5,000 people working, so there are different plants. So this is our second plant over there. Again, we are utilizing our own, producing our own power and our own energy over there. This is the ATS project in China for the chip manufacturing, which is a very, very complicated process, and as you may know, chip production requires high reliability, and we have supplied our equipment. So some of the other examples over here for swimming pools and for greenhouse. This is a better picture than what you saw before. Then this is the biogas installation in Ölfeld in Germany. This is another biogas installation from the cow dung in Germany. On the green meadows of Germany, we have producing the biogas over there. So product overview, you see there on the 4000, we have 2 series over here, the 4000 series and 400 series. And on the 4000 series, we have the 8-cylinder, 12-cylinder, 16-cylinder, and 20-cylinder engine with the corresponding powers given over there. And then we have the 400 series, the 6 and the 12-cylinder engine over here, up to 425 kilowatt electric. The product design is the state-of-the-art design as far as the MTU is concerned. I think from the technology standards, this would be, I would put it as one of the top designs as far as engine technology is concerned, because if you look at the number of engines which MTU produces in the 4000 series, it's about 5,000 to 5,500 engines per year. So this is a very, very modern plant, and here we have the latest technology available. Besides that, from the engine manufacturing side, we do all the maintenance programs, and all the services are available there, and depending upon, sometimes we can also arrange for financing, but that is a different issue. So that has to be looked into individually. This is a typical self-contained model of a CHP, where it is a complete package model, as you can see, with the expansion tanks and everything included into the whole thing, and this can be put in, transported very easily. Actually, the plant control systems, all the systems are there, so you have the visualization functions via touch screen, plant controls, remote diagnosis. So today we can even from Friedrichshafen or from Augsburg or from Singapore, depending upon wherever you are, we can, if you have, we can go into your engine, look into the engine via internet and see and control the engine, and let's say if certain data has to be changed depending upon the circumstances, we can go into the engine and change that remotely. So as far as cogeneration is concerned, this is another example of cogeneration. Basically what you're doing is converting chemical energy into mechanical energy and then into electrical energy, and using the jacket water and exhaust heat so that you have the maximum utilization of energy over here. Cogeneration advantages I've already mentioned before, but basically as it is a repetition of that depending on what kind of application you have over here. So if you see, and this was a very good point which Professor Iyer made before, if you're looking at the big plants, and if you look at the gestation period of these big plants, and the viability of these plants, I think it's highly uneconomical, because you are looking at a time span today for a big conventional plant between 20 to 30 years actually, you see. So based on that 20 to 30 years, you are putting up a plant which is becoming obsolete within the next 5 years actually, if you would look at that. So the concept to utilize energy, I started this as in the US, and at that time I was with Jenbacher in US, looking after their operations in US. And US, although being a very, very modern country, which we believe the transmission system is has its limitations over there, so that we started with the decentralized power and distributor systems at that time. Then we developed that with GE together. Later on I sold that to Jenbacher to GE, and that is where it started actually. From the gas availability, we were in Canada, we were doing some, our concept was to go on power within 6 months, depending upon, so because time is of essence, and today you require power fast, and how to do it. So naturally the prerequisite for that is that the gas availability should be there, as you already mentioned before. But the rest of it is not there. So if you don't have the transmission possibility, then you have all these losses over there, as depicted over here in the chart. The most effective way to utilize power is have decentralized system, and then put these decentralized systems into operation within 4 to 6 months, depending upon the size of the plant actually. So you can easily go up to 25 to 50 megawatts. My biggest plant which I did was 1 megawatt engines 15 times. That was another company called Clark Utilities in the US, and the people are a little bit shy, you see, because of the load sharing aspects. I'm talking a little bit technically over here, and how to synchronize all that, but that's not a problem at all today, you see. So I think that's very easy to do, provided the technology standards are maintained. And we are talking today, when we are talking about 25 to 30 megawatts, those can be put in with small units together. The advantage of the small units is the national system, and this is one of the major areas, because when you're looking today at big power plants running at about 35%, 38% efficiency, I mean, just imagine how much you are wasting energy. This is just crazy. So here is the answer to your 50 gigawatts and how to use the 50 gigawatts in a very effective way, and that is this cogeneration and trigeneration. Trigeneration especially for the Asian countries where cooling is required, is one of the most efficient ways. In Europe, we are mostly using heatings over there, so we are concentrating on heating energy, so we have distributed heating plants and power plants. But here in Asia, where you can use the cooling systems, chilled water system with absorption chillers and so on, that is a big advantage over here. So this is a small diagram of the process which you are doing over there. So we were talking about base loads and peak loads. I mean, it's a very debatable issue. What is the base load here in this country, and what is the peak load? Because we're already with the 25 to 30% gap in the base load over here. Everything becomes a peak. Look at that, you see. So I mean, the question is, what is the policy, and what you are going to, how you are going to apply that policy, and how you are going to price that utilization, which you already mentioned before. Also, I think that's going to be one of the major issues, and here we have to look at it. I mean, this diagram depicts roughly a picture of how the energy requirements are, you see. So it can be a little bit different, and depending upon, because there can be 2 peaks or 3 peaks depending on which region you are working and what are the ambient conditions. But basically you see that on a regional basis you have different forms of energy, and all these forms will be required with different weightage. So here's again one of the another major areas I've mentioned, emissions, and emissions is the NOx emission levels, which we are looking at today. So generally, I think for India it is 500 milligram per cubic meter over here, but and there are certain other areas where they're very stringent about that. So we are looking at 250 and even below those. So this is going to be one of the major challenges to the engine manufacturers, how to reduce these emissions. Although we may be using natural gas, but still we will have these emissions, and that is where the technology aspect comes into the picture. So if they become more stringent, then you will have to use catalytic converters over here, which are very expensive. But there was a very wise Nobel laureate, Robert Koch, who I think he got his Nobel Prize in 1927 or something. He recognized the value of the transaction cost, actually, at that time. And the transaction cost is the holistic approach to the total energy and environmental cost, if you look at that today. And we have to be we talk about being user friendly, but we have to be environment friendly, actually, you see. That is the concept of the future, and that is the heavy price which we'll pay if we don't look after that. So these are the different control systems which we have on the engines over here, and This is just a picture to show how the interfaces can be done and how you can communicate different data and transfer that data to the various places. I already mentioned our representative for gas systems is Maxwell Energy Systems in India, and India is being looked after from Singapore, where I have an office, and Mr. Stephen Nang is working with me together over there and looking after the Asian region over there. I sit in Germany and in Singapore and shuttle between the region over here to see wherever I can be of some help. So, ladies and gentlemen, thank you very much. I hope this has given some new thoughts about the utilization of the energy, and I think that for India is the best way if we want to realize 50 gigawatts and utilize our resources resourcefully. Then we have to think of all the various energy forms, and this is the only way to do it is with the decentralized energy systems. Thank you very much.
With this nice presentation by Khanna Saab, and the way he showed that MTU has been successful in various other markets where gas has been made available and pricing has been, I would say, economical. We can't say low cost pricing. I've never agreed with anything called a low cost pricing, but there could be an economical, sensible pricing of gas, and if that comes, then it can work out. In between us now we have none other than the Honorable Shri Suresh Prabhu, who had been, in my opinion, the best power minister the country ever produced. Please give him a big hand for that. Yeah, and I think this, while we look at the Electricity Act, the kind of constructive criticism and the way the whole thing moved forward for India after that, I think the whole credit must go to Suresh Prabhu Saab. And this forum must appreciate that. And then he has taken time off. Believe me, I was not even preparing because Anil Rajan Saab, I told you, had a problem and he had to take care of his dad. I was not knowing, who would be now inaugurating. And yesterday he has landed. Believe me, there was very little communication. We could not even put up his name. I was only coordinating a thing, sent an email to him, and he is here amongst us. So you can think what kind of relationship we share as Inertia and me personally, and I have great regards for him. And actually we must hear him on this subject, And before that, since he just came now, I would just put a few points and we would first call him to talk, The whole idea is that we have, in spite of all that ultra mega policy and everything that we do, and the advocate of ultra mega power, we are seeing that it's not reaching where it must. We are not against it. We are saying that it must come again. But then that takes a very long path, 7 years, 6 years, and there are conflicts of interest because land acquisition remains a question even in thermal power. It's not only in hydro. Hydro still goes on because there are multiple benefits to a project. So projects where people realize it, it will come through. We see that this kind of land acquisition problem may not arrive in solar, although it needs land, because the kind of land usage is very different. In the case of decent also, we don't have any problem because smaller power plants can go through in both urban and rural locales, and very large land mass is not required, in a decentralized station. That's one. Second, we of course put across that transmission, I would say, bottleneck is going to, I tell you, stall everything, because even in Delhi when we are discussing, when all these plants come up, I don't know how they would take it away from the grid. Because today we are still limited to that 35,000-40,000 megawatt capability to wheel and transmit power. And I don't know how much we'll expand. And we are going to add like 1 lakh megawatt, 2 lakh megawatt. And where is the grid capability to send all that electricity across? So again, we will be stuck with regional capacities. So decentralized power is an answer for that. The third part is for sure that why not clean and green power which can come fast onto the local grid. So these are the issues, and then have a good target, 50 gigawatt. Like we on 20th July we discussed 40 gigawatt, the real mission. I was a little, that day also I was a little shaky, but all our friends, couple of friends here, and most of them, including Anil Razan Saab, including Dr. Parikh, who's been, I would say, a very active member in the planning commission and had done enormous work, said that is a target perfectly achievable by 2022. And we are saying 50 gigawatt for decentralized gas and biodiesel based power. We're not even calculating the solar and all. We're not discussing that. We're saying, okay, let's say, take an achievable factor and let's say, can we do 50 gigawatt in next plan? And we gave a figure that we are already seeing 15 gigawatt coming from captive and decentralized in this plan already as of date, which is in the Power Ministry's website. So we are not talking out of our hat. We are only, reinforcing the fact that it could be doubled in the next plan, and we could see this kind of power coming onto the local grids and really able to solve our crisis in the short and medium term. And definition of medium term, I said, was 7 years, path. And I'm not saying that we will discontinue it, but this model can be taken to rural after tackling our urban crisis. And we're saying biodiesel could be a great chance or opportunity for us to do the next round, with all this little bit of a, I would say, 24/7. And I don't know how do they give 24/7 unless they plan something like what DLF has done. So let us hear the DLF case before we move on to Agrico's power rental solution, which is also an amazing and interesting solution that can come. Mr. K.K. Bhattacharya, please.
Good afternoon, ladies and gentlemen. There are two ladies there, okay. Before I start this presentation, these are most technical and other things. I would like to elaborate or rather explain what Mr. Prabhu had just given the problems of the power houses. See, this decentralized generation and whatever we have done, we call it a cogeneration plants in Gurgaon, and our experience, we have been doing it for last 6 years, and now we are operating and producing approximately 100 megawatt of power and approximately equivalent power of 20 megawatt of utilizing waste heat of those power generations. The problems which Mr. Prabhu touched are, I'll go one by one. The first thing is land. I would like to say that we have not used any surface land for this making 100 megawatt. This is all underground and in the basement of the buildings, and those buildings, basements, it has to be made for some purpose of parking or other services. We have utilized that area only. So land problem goes. Now second was water. We are talking about the urban situation. Urban situation, the water which is domestic water, approximately 70% goes waste in sewage. That 70% water is a huge water, and the sewage treatment plants are not non-existent. This goes to the drain or to the rivers, polluting the whole area. And in the whole period of water crisis, we are just wasting that water. Our plants don't use any municipal or any river water for running those plants. These were whatever water is required, we use from the STPs. We have established sewage treatment plant, and the entire population, whatever they give, about 50% of that water is used for the power generation part of it. Then third thing is transmission. It's obvious, you don't need any transmission lines and all here. Then local distribution. Local distribution really has a problem. In the urban areas, and as per the Electricity Act, you can distribute the power only if you have got distribution license. Now, getting a distribution license is an impossible task these days because it is all monopolized by the government authorities. We have been trying for last 6 years to get a distribution license in our area, which is not being given only because of one reason, that one line is written in the Electricity Act, that it should be a revenue area, it should be a municipal area, or it should be a large urban area. Now, our interest is only the area which we have developed, and that is approximately 5,000 acres, which falls short of about 100,000 acres from the entire municipal area, what is the municipality is operating now. So it has been disallowed. I have seen the present licensees ARR last year, and it is mentioned very clearly that the distribution losses, I am not talking about transmission, distribution losses in that area, Faridabad and Gurgaon, starts from 40%, and amazingly in one area it is 98%. Why are they producing at all? Why are they distributing at all? If they are only utilizing 2% of that air hour, and out of that maybe 70% will be theft. So these kinds of problems can be managed by support from the government only. We can do so many things. We have created 100 megawatt. We have utilized waste heat. We have utilized wastewater. But I don't find, last 6 years it is my mission. I am going all over the country and telling people why you should do it. But nothing has happened. There are three problems mainly. One is gas availability, of course. Number two, large investment. And number three are all sorts of regulations of the government. So people don't want to invest that kind of money in this kind of thing. With this, I'll just start my... This slide have been discussed. Professor Iyer also mentioned that we are making mega powerhouses, bringing power from a longer distance, and then losing approximately, if you do very, very well and no theft and all, only technical losses will go to around 35%. If you do cogeneration, which is below, this cogeneration or a decentralized generation, this losses can come down to approximately 5 to 6% only. That mainly because of the distribution portion of it. So one thing is very clear in that. Say you make a 1,000 megawatt station. You use, say, 1,000 units of gas. And if you put 50 megawatt station or 20 numbers of the same capacity with the same gas, you will be using 30% less gas, at least 30% less gas for the same power what you will utilize. That is a great saving. Apart from that, waste is a waste. Now, this is the consumption pattern what we have found out in the urban areas. Residential and commercial building consume 25 to 40% total energy use. 30 to 40% of global greenhouse gases emission. Typical energy energy consumption is shown this way. 60% of the goes in air conditioning. In present urban areas, I have taken NCR data. And other balance are other things. So what we have done in this case is say we are putting a large building. In that we have got reciprocating engines. It can be diesel or gas. And then it can give heat energy and cooling energy by the absorption heating. In our case, we have used natural gas, which is really RLNG, not normal. This thing is coming out from the imported gas. These are our plants are mainly cogeneration plant. These are feeding the building. We are also interested to give the surplus power to the area developed by us, but it has not been allowed because of the distribution license problems. So we are operating our plant at a much lower load factor. But even then, it is the payback is not very long. We got at least first 10 megawatt plant has given the payback we have got in 1.5 years. The additional cost. This is the power flow. There is a gas engine or gas turbine. It goes to alternator. Then alternator, the turbine exhaust goes, if you don't use is just for chilling or heating. Then it goes to VAM, and then chilled water and power is supplied to the building. Now this is the comparison. In the conventional system, in this plant, say it is 10 megawatt plant which we have done, which is doing its job, we would have done 12.25 megawatt power would have drawn. Air conditioning, we got 4,000 tons, and heat energy and flue gas is allowed to be released in the atmosphere. In this, what our system we have done is the cogeneration is, We have put electrical power station of 9.8 megawatt. The AC air conditioning chilled water availability from that plant directly only from the wastage is 3,500 tons. Equivalent electric energy saved due to that 3,500 tons is 2,450 kilowatt. So percentage of energy saved is 20 to 25%. Overall system efficiency has gone to 70 to 90%, though we are not getting because of the low power, low load factor. It is in any case getting about 70%. Annual energy saving is 1 megawatt from the conventional system. Now this is a case study. Base case electricity and cooling demands are met through grid power and electric chillers. Annual energy consumption in this plant is 450 megawatt for 50 lakh units. Annual energy saving approximately 80 lakh units. And if we have the residential and commercial both connected with this, we can have much better load factor here. In a similar type of plant, say if you take the power from outside and also get our project case, the installed capacity required will be in base case as shown here. So in place of about 55 megawatt, you can manage with 35 megawatt only in the same area. So load factor goes like this. You get about 70% load factor, easily 70 to 75%. And in other case, even with very good utilization, you cannot get more than 50-55%. Energy consumption I have already mentioned. In the same capacity system, we can utilize the electricity up to this thing about 350 MU, and in this case only about 240. Now economics. The decentralized system of the similar type with the cogeneration unit, of course, the cost, our cost has come to 4.5 crores per megawatt. In the conventional, it is 3.5. It's definitely costlier. Operational cost, if the gas within 20 cubic meter per, 2 rupees 20 per cubic meter, and HSD today is 40 rupees a liter in NCR region. 5 rupees is the variable cost. And in conventional system with the diesel, it will 9.5 to 12 kilowatt hour depending on the efficiency of the engine. Depreciation benefits you can get up to 80%, and conventional is 20 to 30%. The carbon credits can be earned about 2,000 CERs per megawatt, and in conventional is not eligible. Space requirement is much less, it is very high in conventional. Layout options are there. You can have multiple powerhouses of, depending on the area, from 20 to 50 megawatt. I would not recommend more than 50 megawatt because then it becomes difficult to control the system. But less than 20 is also not viable. Then you can interconnect those systems to have a better efficiency. This is the area, we have got a place called Cyber City in Gurgaon. This is the area which is about 160 acre and mainly of IT related buildings, large multi-storied complex, and all multinationals are there. We have got 10 megawatt was the pilot plant. Then we made a small 6 megawatt plant also using only, these are 10 and 6 megawatts using only gas engines. And then we had 240 megawatt plants in the same area. These are, we have used gas turbines and gas engines. Gas turbines are limited to up to 5.3 megawatt and gas engines are all 4 megawatt machines. Out of this, first 340 megawatt, 6 megawatt and 10 megawatt is already operating. The last one is under commissioning at present. Now, we have gone through various forums and also some data and all. This, as a conservative estimate, of total decentralized or CHP potential based on existing building stock data is about 3.4 gigawatt today. If all the potential were realized, then about 18 metric ton of CO2 per year could be displaced in India in cogeneration system only. This is a carbon mitigation thing, which I will not go in detail. Now barriers. Assured gas supply at reasonable price. This is an area which is this decentralized or cogeneration is not recognized by any forum. Rather, GOM also never recognizes it. They are more concerned about mega power plants and also fertilizers and other places. So we have to buy gas at a very high price. When we started the plant in year 2006, the gas prices we are getting about 9 to 10 rupees a cubic meter, including taxes, transportation, everything. Today that is approximately 18 to 19 rupees. In area where the CGDs are not there. Wherever the CGDs are there, is much more, much costlier. In Delhi, particularly, it is 23 rupees a cubic meter. So whenever you just compare with the government power or the grid power and you compare this power, naturally the investor feels this is non-viable. Then availability and treated soft water. That is another problem. In our case, we have managed with STP, but everywhere people cannot do that. Utilities, third parties, utilities do not recognize it. So this is not taken as energy program. Then policy of purchase of them for having a proper, you call it a profit or whatever margin, you must have the proper load factor for this. You've got enough surplus power available. But neither power exchange or nobody is ready to give that kind of power. Today the power exchange prices maximum is about 4.5 to 5 rupees. Today's price is 4.5. I've just got a mail just now. Is 4.5 is maximum and average 2.2. And with these gas prices, you cannot produce profitably the power as less than 6 rupees and 50 paisa today. Now, our mostly areas that owners of the they don't want to put cogeneration plant. As the main objective is to make the building and for the lowest initial cost. Decentralized puts additional cost burden. So people don't want to really do that. And I have talked about the regulation. This is also a barrier which cannot be overcome easily. Thank you.
Thank you, Dr. Bhattacharya. It was a good insight on the studies and the barriers you have indicated. And on the next speaker, I would request Anthony Schmidt to come forward and speak on the session. Thank you.
Arora Sahab, we'll just take 1 minute because Prabhu Sahab would be leaving. So I think we will like to give him a memento. And may I request Hridesh Khanna Sahab to come over and give this memento to. And I think Anthony can continue with it. And we should thank Suresh Prabhuji, all of us, please. Thank you.